All right. So what we are going to be talking about today, we're going to continue on with this idea with modal resonance, and like it's hard for me to understate how important this section is. This is one of these ones that feels like abstract and odd, but once you get the hang of this stuff, this is probably one of the more important things you need to understand with acoustics. And actually, if we can get through our slides today, I'm going to pull up some examples of using Room EQ Wizard so you can see kind of the effects of this thing. But yeah, I guess actually there is a pretty cool little thing I want to get to with Room EQ Wizard today. So if I can get to that, we'll crank through it. So let's get this show on the road, and we'll continue on with this. So so I'm still talking about so basically what we're doing is we're talking about low frequencies in small rooms. And just to recap, rooms resonate like whoops, I need to pull up my chat window. Where's my Zoom at? I didn't start sharing my screen. That's why this is. Okay. Samuel, you got a question? Sorry, I didn't have that thing pulled up. Oops, shoot. Okay, that's all good. Let's pull up a chat. This window combination thing is funky. Cool. All right, so let's back that up. So we're doing modal resonance. Okay, so yeah, so we're talking about low frequencies in rooms. So what we want to look at here is like yeah, again to recap, is that rooms resonate and they ring, so to speak, and just like a guitar string. And we've gone through, and the frequency in which they ring is dependent upon the width between the walls. So we just basically did to reiterate, we did this two wall resonance here. So if we look at this in terms of pressure, probably should have drawn this as a box, but looking at that simulation we had where basically the air is swishing back and forth, we can think about that in terms of air pressure. So when all the air is sloshed over on this side of the room and it's squished up over here, we have high pressure here and rarefied pressure over here, or low pressure over here, and then it's going to go back and forth. And as a result, it kind of looks like it toggles back and forth here. So we can imagine that this standing wave sets up in a room and it just oscillates back and forth at a wave, and it's dependent. The standing wave, the frequency of the room depends on only the length, and I mean you could say it also depends on the temperature. But so in this length of the room, we see that we have 1/2 of a wavelength. So what we say there is like in L equals 1/2 lambda, or lambda equals 2 times the length of the room. So one full wavelength is twice the length of the room, or the length of the room is 1/2 of a wavelength. That's saying exactly the same thing, just algebraically different than or algebraic versions of one another. Okay, so this is just like I'm gonna go back and do this again. It's like I want to reiterate this stuff. So wavelength and frequency. Now that we know the wavelength of the waves, we can calculate the frequency of the modes of oscillation. Good old V equals F times frequency times lambda. So 344 meters per second. Now, all we got to do is substitute. This is the one that I don't know. This creates a mental block for a lot of people. That lambda equals 2L. Remember right here, it says lambda equals 2L. So therefore, it allows us to put 2L as a substitute right there if I want to. So I can just drag this 2L, because lambda equals 2L, that I can do F2L, and that's the way to do that. So V equals F times lambda. F equals V over lambda, and since lambda is 2L, I can just drop a 2L in there. So the only thing for me to figure out the frequency of the fundamental frequency for a room, all I need to know is the length of the room, because we know that this is 344 meters per second. Okay, so we did this last time. We did this before, so we're going to do this again, but we're doing these ones as clickers. So what I want you to do is I want you to go through and do that. So let's bring this in. We're going to do some clickers, get this thing ready to go, and do it. So what I want you to do is basically what you do is, and because we also know that the modes of the room are integer multiples of the fundamental. So all you need to do is find the fundamental frequency, and then you multiply it by 2 and you multiply it by 3. So that's all you really need to do there. So I imagine everyone's getting their clickers fired up right now, but I'll give you a couple minutes to do this. In the meantime, if you have any questions, shout them out. So I'm using feet in this one. I'm going back on my word, and I said I'm only using um, I'm only using metric in this class. But truth is, we have to be able to, in real world, we have to be able to convert between both. So use 1130 as the speed of sound, or V equals 1130. I really want you to be good at this part. Yeah, sure. You got it. Good question. So the question was, are we only paying attention to one axis, so to speak? And the answer is yes. We're about, in just a moment, we're about to look at all three axes. So you're right. And so looking at this only in one axis is only give us one part of the story. We need to actually do this analysis in the X, the Y, and the Z. So in a normal room, when you do a modal analysis, you're going to basically take a tape measure out, or in the case, like what I have is I have like an ultrasonic tape measure thing, like a distance measurer. So I'll walk in and I just hook it up and it measures the distance between the walls. So I don't have to like do a 30-foot tape measure. It can do this thing with a laser, and it's really useful. And then I can basically just do V equals F times lambda, and then I can do this multiplication, and then I do it in the floor to ceiling, and then I also do the other wall, front to back wall as well. You can also set this up in like a spreadsheet pretty well. Hey Noel, did you get logged in? I just saw your chat. Cool. Anybody have any other clicker technical issues? Beautiful. Okay. It's hard because this is one of those things that like I'm going on faith. Like when we're in class and we're working together, I can see kind of like what the issues are on other people's screens and stuff. But when we're doing this, it's so much harder for me to see what the technical issues are. But it sounds like it's kind of working for most people. I've got 49 responses so far. How many people we got right now? So just as a heads up, so if you have critical listening with me next semester, I use clickers all semester. So get used to this, where you're going to be seeing a lot of this. Has anybody used clickers in any other classes? Like you find these a lot in the sciences. Cool. All right. We're coming up on 4 minutes. We have 2 more questions exactly like this one. So let's go ahead and do last call on this one right now. Let's call stop. All right. And the answer is indeed B. So I don't think I have it. Like, let me close this one up and let's do the math on this thing real quick. So I'm going to do it with I'll do it with the whiteboard. I'm going to have to do it with crappy handwriting. So I apologize, but that's the way it goes. So the way this is going to go is I always go V equals F times lambda. Then I'm going to go, the reason I start with this one, because this is the way I can remember it. It's too hard. Like it's just easiest for me to remember it this form, and I'm solving for F. So I go F equals V over lambda. And then this we know is 2L. So I'm going to go F1. The little 1 right here indicates that it's the fundamental, V over 2L. So F1 equals 1130. Because we're in imperial system, we're using feet. And so, because this is actually, so if I want to do a dimensional analysis on this, it'd be feet per second. And then the bottom, this is going to be 10. Sorry, I know this is really bad handwriting with this thing. My handwriting sucks anyway. Times 2. So F. I'm doing it very explicitly right now. So 1130 divided by 20. And I've got to do my calculator here. So I do 1130 divided by 20 equals 56.5. 56.5 hertz. So F2, I don't know why it's blue, but F2 equals 2 times F1 equals times 2, 113. And then F3 equals 3 times F1. Yes, divided by 2. Okay, so was it 56.5? 3. It's 169.5. 169.5 hertz. Sorry for the crappy handwriting. Any questions on that? Okay. The answer is 56.5. Yay. Let's do it again. Now I'm doing it in meters. What are the frequencies for the first 3 modes of a room that are with walls that are 6 meters apart? So now you use 344 instead of the other one, instead of 1130. So all you need to do is find one number and you've got it. We have one more question of this after this one. I think we might have one more clicker after this later today as well. All right. Let's try to get this one a little bit quicker. Let's see if we can get this in within 2 minutes. And even as it approaches, even worst case scenario, always guess. Like you get points for guessing. You get more points if you get it right. But you get points for guessing. All right, 10 seconds. All right, last call. Wait, how did it? My responses dropped. That's weird. Okay, cool. You can always change your answer too, by the way. So like that's just the thing with the clickers. Is like if you click in and you can always just change it if you needed to. All right, let's take a look. I believe the answer is indeed A. So basically you do 344 divided by 2 times 6. So it's 344 divided by 12 is 28. 28 hertz. That's pretty low. But these are all like that's probably like in the inaudible range, but it's getting there. All right, let's do one more. What? Oh, okay. I forgot to change it. It's switch up. I guess we're not doing the third one. Well, okay, let's do it. But there's no clicker. There's no clicker with it. So okay, this was supposed to be. I was supposed to change this one. Oh, actually, I did change it. Okay, let me do this. When is this one? I didn't change this one right here. I didn't change the thing for it. That are 25 feet. Feet. Okay, there it is. So what are the frequencies for the first three modes for walls that are 25 feet apart? So this is a much larger room, and you'll see why we're talking about this in a minute. So I want you to do this one again. One more time. So we're using feet again. So remember, it's 11:30. So we have 2 minutes to do this one. So I'm hoping, I saw that, we have a number of folks that are still like kind of getting them, that aren't getting it right. And so if you have any questions, please, like, let's try and iron out those kinks and figure out why you're not getting the right answer. Because I feel like at third time through, we should probably have a good grip on this. Honestly, that's why we use clickers, because clickers are for teachers, because they give us feedback how the retention's going. All right, 10 seconds. We're missing one person. There we go. 52. Cool. Last call. All right. Answer is C. Whoops. Where'd that go? Oh, it crashed on me. That's weird. Okay. Well, I'll have to go back and figure that out. But it indeed was 25 feet apart. Okay. So let's do a quick comparison. What's going on here? Sorry. My clicker is being strange. All right. So let's do a quick analysis on this here. So this is the quick math. So these are the ones we just did. So 10 foot, 6 meters, and 25 feet. And we did this. So the answer was 56.5, 113, 169, 28, 57, 86, and 22, 45, and 68. So what we can see here is that as the room gets bigger, the frequency goes down. So this is, whoops. Is that right? Yeah, 22.6. We can see that as the room gets bigger, the frequency gets lower. And then, of course, because the fundamental is a lower one, the multiples are also lower. So a 25-foot axis room, this is well below, well, I wouldn't say well below, but this is like nearing the threshold of hearing. We wouldn't be able to hear this one really hardly at all, unless it was like ridiculously loud and everything is vibrating in the room. But we could hear 45, and we could certainly hear 67. But as the room gets really small, so like a 25-foot room compared to a 10-foot room, we can see that this is 56, 113, and 170. These are totally audible. These ones are going to be pretty stinking low down there. They're audible, but they're way down there. So we can see that this room mode issue becomes much more audible in smaller rooms. So the smaller the room, the more apparent these room modes are going to be, because these are going to start reaching really deep into the audible range, whereas these ones are going to be much lower. Now, of course, the harmonic series keeps going and go higher and higher and higher, but in general, what ends up happening as I mentioned last time that the width, the height, like, so if I was measuring the side from wall to wall, this axis, I would say that the height of the room and then the width of the room really don't matter. But as I go up in higher harmonics here, basically the room modes don't really set up as in the super higher modes of oscillation. The first 3 or 4 modes, those ones are going to be the most important ones. Like, and as we go higher and higher and up, they basically smear and they don't really work as well. So we're not going to get quite as many, the room modes are not going to be quite as apparent. We'll talk about what that means here, like what that actually means in just a minute here. So what we want to do now is I'm going to change this over and talk a little bit. This is how we draw, like start drawing things like an acoustician. So this is taken from the book right here. And remember, I'm going to go back to whiteboard here for just a minute. Cause there's my whiteboard. Over here. Bring my little toolbar so I can actually change colors and stuff. How do I clear? Clear all drawings. Let's draw and let's do color. Let's do dark green. So in a room, remember what we did is I was drawing it like if I have just as an axis, the pressure plot is going to look something like this. But what we're going to do is, as the way acousticians tend to draw stuff is what we call rectified. So drawing a rectified wave is going to look like this. All I'm doing is drawing the top half of these 2 waves right here. Because we know by just definition that this is going to go down and up. But what we're doing is we're just drawing the first one right here. So this is how we're going to look at the first mode of oscillation right here. And so even though we know it kind of goes like this, so that we still have 1/2 of a wavelength. So in this case, we still see 1/2 of, oops, let's do 1/2 of a wavelength. So when we talk about this, the way we draw things as, oh, you're not seeing anything? It's sharing now, like something, oh, it's on pause. Yeah, pause the share. Are you seeing it now? That's weird. I've never, oh, there's this like, I've never done that before. Pause my share. That's strange. Okay, sorry about that. So let me do that again. So we draw our box, and if I draw this in terms of a pressure plot, it looks like this. But what we're going to do is we're going to draw what's a rectified wave. So the rectified wave is just drawing the top half of the wave. Actually, what we could do, the technical way, the term of what we call rectification, is if I draw this wave right here. So we know that at any given state, it's going to be up on one side and down on the other, and it's going to be toggling back and forth between these. Not toggling, but like fading back and forth between the 2 of these right here. And then this is going to be our like line. What rectification means taking all the negatives, turn them into a positive. So if I draw this to look something like this, oh boy, that's ugly. Let's redo that. What I'm doing right here is this is still L equals 1/2 of a wavelength. So essentially what we do is we have L equals 1/2 lambda. So this is the way we tend to draw things as acousticians way more, because it tends to like correlate better to how our perception works. So if we get back over to our presentation, what we see here is that they're drawing it like this. But basically this is 1/2 of a wavelength. So F1 equals V over 2L. So that's 1/2 of a wavelength. And then we see our second mode of oscillation right here. So this is how we tend to draw things, even though this is just a rectified wave. So this second one right here, it would normally go down, back up. So rectifying means taking all the negatives, turning them into a positive. So this is just a different way of looking at this. And so perceptually what happens, if I was a little person walking around in this room right here, what's going to happen is if I get near this wall, it's going to be super loud. So this correlates to like our pressure. This is a pressure antinode, and this is a pressure node, pressure antinode. So if I get near this thing over here, it's going to be loud over here and quiet here and loud over here. And then for the second mode of oscillation, perceptually, if it's loud here, quiet here, loud here, quiet here, loud here. And conversely, loud, quiet, loud, quiet, loud, quiet, loud, quiet. It keeps going, but like I said, as I keep going up into the like fifth, sixth, seventh, eighth mode of oscillation, this thing gets a little bit less apparent. But we see that for every single one of these, there's the antinode at the wall. So there's an antinode at the wall over here. And what I encourage you to do, so do this for your room. What I want, like, if you have a room, and especially if you have a subwoofer, this is a lot of fun to do. Basically, it doesn't have to be a sub. You can just use any speaker that goes pretty low. Figure out the modal analysis of your room, and say you're in a 10-foot room, and we know that the 10-foot room is like 56 hertz. So then what you're going to do is take your speaker, go put it in the corner of that room, and walk around the room, and you'll totally hear this. It's incredible. It's when you're playing music, you think it's not that important, but man, all of a sudden, so try it with just that. If you walk around, it's like, I can hear it. It's completely gone. I can hear it. And if you walk back and forth between that wall, this is exactly what you'll hear. And then you calculate the second mode of oscillation and just go through and do it. It's one of the more wild things here. So all I wanted to do here was do a little bit of the math here to show that F1 equals V over 2L. So F2 equals V over L, because this is one wavelength right here, which actually equals 2 times F1. This is just some algebra, but all you really need to care, the most important thing you need to understand is that if I solve for F1, I can just calculate 2, 3, 4, 5 by multiplying it by 2 times 3 times 4 times 5. That's all we really need to know. So the integer multiples of the fundamental. So the pressure nodes are always at the walls. So, and there's, well, I don't know why I said middle of the room. So in the middle of the room, we have odd harmonics. So in other words, so we have odd harmonic nodes, because at this one, this is the first and third have a node in the middle of the room. And then the second mode and the fourth mode are going to have antinodes. So even harmonics have antinodes. So this is going to be kind of a weird thing. So if I'm playing music, I'm not even going to hear any of the first or the third mode based off that room. And it's hard to explain this, but it's like it just doesn't exist. Like that, there's a giant EQ notch out of that at 60 hertz if you're in a 10-foot room right there. It's wild. Okay, so let's keep talking about this. So we have other room modes. So what we're doing right now is we're going to, this is going to get a little more complicated, but don't stress out about this. So we have what we call axial, tangential, and oblique modes. So our axial mode is one that goes like this. It bounces back and forth, back and forth, and back and forth. By far, these are the most dominant nodes. This is the one that we care the most about. Tangential modes, so it basically bounces there, 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 there. And so it basically sets up a wave that bounces around the room. So in one axis, so this is one dimensional. This is a two-dimensional one right here that we call tangential. And oblique is where it bounces up to the ceiling, to the wall, down to the floor, back up. So like oblique are going to be three-dimensional standing waves, two-dimensional standing waves, and one-dimensional standing waves. And like I said, these are by far the most apparent. These ones right here, they exist, but they're not really that important. It shows up in our plots here in just a second, but I'm gonna say that it's with the exception of some certain cases, this is not really that important. So as wavelength nears the room length, rays fall away. So in other words, those modes as the modes get smaller and smaller and smaller, as the modes get higher and the wavelength gets smaller, they basically kind of fall away. So axial is the most important for small room acoustics. So this is taken from the book, and I'm going to show it to you, but we're not going to really use it in such a way. So like I said, we want to start thinking about this in 3 dimensions. So the way I do this is the way I do a room mode analysis is I'll measure in one, and I usually have a spreadsheet set up for this. I'll basically just set this up, and if I type in the length of the room, it'll give me the modes of that in that room. Give me the modes of that axis. Then I do it in the X, like I'll do the X, the Y, and the Z. And so we have to think about, each axis has harmonics there. So they have this one right here. It's called the room mode equation. I'll show it to you. We're not going to actually do the math on this. You don't really need to worry about it too much, but it's kind of interesting here. So C being the speed of sound. So 1130 or feet per second or 344 meters per second, depending on which one you use here. So P, Q, and R is going to correlate to these integer numbers right here. So P correlates to the integer on the L, Q correlates to the integer on the W, and R correlates as an integer to the height. So we basically, if you just do like a 0, 1, 0, like you can put in zeros here, or you can put in 1 or 2 or 3 or 4 or 5, depending on which mode of oscillation you want to work on there. So, and this will tell you essentially the frequency that this happens at. So the result is it looks something like this. So I'm not going to really do the math for this right now. I don't think it's that enlightening. There's other things that I think are more important. So the concepts are more important than the math in this case. So if we look at this thing right here, what they did is they plugged these numbers in right here. So what they're doing is they're looking at the one we call the 100 mode. So the 100 mode basically says I'm looking at the first mode of oscillation in one axis and not the other axes right here. So this is an axial mode right here, and it shows up to, so this is for this room dimension right here. So this is a room that has a 12.46 feet by 11.42 feet by 7.9 feet high. And the result is, if I plug those numbers in, I get a 100, I get a 45. So you can also just, the other way you can look at this is if I just F equals V over 2L, and L is, I don't know which one they're doing here. So this is P. I don't know which one they're defining as P. But basically, this is my axial. So one of them, the first mode is going to be 45.3. One of them is going to be 49. Like in this direction, we'll just say it's 45.3 in this axis, 49.5 in this axis, and 71.5 in this axis. This one right here is, if I did, it's called the 110 mode, and that's a 67.1. So that's a tangential. That's one of the one that wraps around the room. And then we have a couple more tangential ones right here. Then if we add the second mode of oscillation in the x-axis right here is at 90.7, and just going through. And basically what they're doing is they're just plugging in P, Q, and R into that equation, and also the lengths, and you get these frequencies right here. And what we can see is that there's a bunch of these frequencies, but what I care about most is this axial line right here. Not that I don't care, but these ones are not going to be very apparent. The reason being is that every time it reflects, it's going to lose its energy a little bit, and so therefore these ones are going to not be as strongly present as these axial ones. The axial ones are really, really present right there. Dawson, so the question is, does the location of the sound source affect where the nodes are at? The nodes are? No. So basically, it doesn't matter where the sound source is that creates it. It's the room mode itself is just the way the room excites is basically going to excite. But I will say that if you want to excite the room modes, you do that best by exciting it in the areas of pressure antinodes. So in other words, if I want to excite the room modes, I basically put a subwoofer against the wall. Actually, putting it in the corner is the best place to excite the room modes, but the room modes are kind of bad. So it doesn't really, the nodes never change. The nodes and antinodes never change because they're a function of the standing wave of the length of the room. But how much I excite them can be excited by where I put the sound source. But the nodes and antinodes do not move ever. They're fixed based off of the dimensions of the room. So cool. All right, we're at 11:39. Okay, let's get moving here. Like I said, these are important, but this is by far the most important. I focus on pretty much strictly axial modes. So I do a spreadsheet, something similar to this, but I don't do this like P, Q, and R business. All I do is that thing that we just did at the beginning of class with the clickers. I do that for like the first 5 modes of oscillation for each of the different, axes. Okay, so why are nodes bad? So it creates uneven sound for different parts of the room. So axial nodes cause frequencies to vanish. So most control room seating is near the middle of the room. So I'm sitting right now in my room, I'm sitting dead center because I have a bunch of speakers over there and I have couches behind me and my room isn't all that wide. But the problem is I'm sitting at a place where we know that all the odd harmonics are going to be gone and all the even harmonics are going to be really represented. So this creates some real problems there. So axial modes are the most prominent, as I keep saying. So let's take a look at that. Let's plot this out and let's talk a little bit more about like what this thing looks like. So what we're going to do first is look at this thing. Visualizing the modes is very, very effective when paired with the math. So seeing is believing. So what we have here is what we call the 100 mode. And we already kind of talked about this right now. So this is like this is the P, Q, and R. But if this is the one, this is the mode. What we're looking at is in this axis right here. This would be, we're not looking at any modes in this axis, and we're not looking at any modes in the vertical. So all we're looking here is we're drawing this thing rectified. And what we can see that at the wall here, it's going to be an antinode, but we can imagine this thing going all the way back. So what we're going to do here is we call this a 100 mode. And so it's basically showing it right here in this mode right here. So if I did the 0, 1, 0 mode, it would be drawn down here and going in this going back and forth in this axis over here. If I did the 0, 0, 1 mode, it would be going in this axis going up and down. So it'd be going, you'd see the swoop right here. So we'd see there was an antinode at the ceiling and an antinode at the floor. In this case, I have like, I'll call this the front wall, this the back wall, and I'll call this the right wall and this the left wall. So we can see that over here, we have an antinode at the left wall and an antinode at the right wall and a node in the middle of the room. And then if I were to go in the 0, 1, 0 mode, I would see that I have an antinode at the front wall, an antinode at the back wall, and a node in the middle of the room. And then the same thing, if I did a 0, 0, 1 mode, I would say I'd have an antinode, a pressure, this is important, it's a pressure antinode at the ceiling and a pressure antinode at the floor. And if I was standing up, like if this was say like a 8-foot room, if this is an 8-foot ceiling, that the 4 feet up in the middle of the room would be where the antinode is. Or sorry, the node is. My bad. So let's look at another one here. So this is the 3, 0, 0 mode. And so we're disregarding these two other modes. We're just looking at the third mode of oscillation. So we have an antinode, node, antinode, node, antinode, node, antinode. So, and like I said, if you do this, try doing this like it's the 3, 0, 0 mode. Set up speaker in your room, or you don't even have to move your speakers. Just play 60 hertz or whatever it is. Figure out the room mode and walk around your room, and you'll hear it go play as a sine wave, and you'll hear it go quiet, loud, quiet, loud, quiet, loud, quiet, loud. Like it's crazy. It's so bizarre. But just knowing that exists, it's freaky because you're like, man, that's affecting my mixing. That's affecting this. And so if I was sitting right here versus sitting right here, like in the room, it's wildly different. I'm going to have a different experience between these two different spaces here. It's going to sound thin here and bassy. Well, we'll say it's going to sound thin here and bassy here and thin here and bassy here. So it's crazy. So now what we're going to do is we want to flip this thing though. And this is like, we want to start looking at more complex versions of this thing. So if, say I want to do the 3, 1, 0 mode. Well, it's kind of hard to draw. Drawing in 3D is really difficult to do. So we need to come up with a better method for drawing these things. And what we're going to do is we're going to look down on this. So if I look straight down on this thing right here, we can draw essentially topo maps. And so if you've ever looked at and we did this when we were talking about the equal loudness contours, but if you've ever looked at a topo map, and you can do this on even Google Maps, right? Go to Google Maps, and if you hit the terrain tab, like the terrain visualizer, and you zoom in at the right height, you'll see that you can look at the elevation lines, and their contours. So it means it gives us a representation here. So what I'm going to do is switch this over here. So now what we see is that this is an antinode, this is a node, this is an antinode, this is a node, antinode, node, antinode. So it's kind of going down, up, down, up, down, up. So this is basically, we call this a coefficient. So this is like how loud it is and how quiet it is. A coefficient of 1, meaning it's at its maximum. This is at its minimum, maximum, minimum, maximum, minimum, and maximum. So now what we want to do is let's look at this right here. So this is the 2, 1, 0 mode. So we can see that we have the second mode of oscillation in this axis right here, and the first mode of oscillation in this axis right here. And we're not looking at the height. Height is, we can't draw like with standard 2-dimensional drawing tools. This is pretty tough to do. But what we can see here is that I have an antinode here, an antinode here, and an antinode here where it's 1. And then I have a node right here for this line and a node right here for this line and for this line right here. So the result is if I walk around this room, it's going to be really kind of quiet in this area here and here. These frequencies are different kind of from each other, but we can kind of see these are the contour lines right here. So it goes from 8. These are 0.2 coefficient contour lines. So you're not going to have to draw any of this stuff or anything, so don't worry about that. But it's good to understand what's going on here. So we can see that we have multiple nodes. And so again, we call these like hot spots over here. And these are going to be dead spots along these other spots over here for this one frequency. So, and these are for standing waves. That doesn't mean, so if I'm playing a frequency that's like say this is like the first mode of oscillation is 50 and the second mode of oscillation is 100. If I play 60 hertz, 60 hertz isn't affected by this room mode stuff. The only thing the only frequencies the room modes affects are the ones that are actually the standing wave frequencies. So yeah, it's kind of weird to think about it. So in other words, if I had a 50 hertz as my fundamental, 100 hertz is the second mode, and 150 hertz is the third mode. But if I play something like 75 hertz just plays normal out of your speakers, and it doesn't excite the room. It does. I mean, you have reverb and that stuff, but it doesn't excite the room modes. So it doesn't really fall prey to this effect right here. This only affects the certain frequencies that are done by the standing waves. So yeah, it can be kind of weird. All right. So, let's see here. Oh yeah. I was like, whoa, am I done with my slides? Let's ask this one. Where is there always an axial pressure node for an antinode for every single harmonic? Type it in or yell it out. What do you got? Where is there always an axial pressure antinode? That's a mouthful, but it's super technical sounding, but it's good to know. So yeah, Jacob, not quite. So the walls, yeah. So it looks like the people are saying that the walls. Indeed, there's always a pressure antinode at the wall because the air molecules can't move that. So it's at the walls. So in 2 dimensions, where are there always pressure antinode for every single harmonic? How about this one? Corners. I don't think anybody wrote this one down yet. It's the corners. Because we know that we have a pressure antinode in this axis and a pressure antinode in this axis, that it's the walls. Where the walls intersect, there's always a pressure antinode in the corners in 2 dimensions. So how about in 3 dimensions, where is there always a pressure antinode for every harmonic? The 3-dimensional corner. So when I say a corner could be like so at the edge of a wall, like where 2 edges meet, that's a 2-dimensional corner. But a 3-dimensional corner is where the floor, the ceiling, the floor, the front wall, and the side wall intersect. And if you wanna experience this, just start bumping some music and go put your head in the corner. Like literally, go put your head in the corner of the wall, in the corner. It gets so bassy. It gets so big. This is for like a small, like a reasonable small room, playing with some decent speakers. You'll be able, it's insane. But I mean, you can just experience this by bumping some tunes and go put your head next to the wall. Like just go put your head against the wall and you'll hear this. Yeah. So, and so it's crazy how this thing works. So yeah, this means that standing waves have antinodes in the corners always have antinodes in the corners of the room. The nodes are going to be they're going to change based on the harmonic as you move around the room. But the low ones are like the first modes are always going to be in the middle of the room. So the node, meaning it's not there, is going to be in the middle of the room for all 3 axes for the first mode of oscillation or the fundamental. Okay. Yeah. So put your head in the corner. It's super huge low end. Okay. So let's do what are the frequencies? So I'm not going to So what are the frequencies? First 5 modes for walls that are 15 feet apart. Blah blah. There they are, right there. What would you experience in the middle of this room? So in other words, if I walked in the middle of the room, I would hear I would hear no 37 hertz. I would hear a lot of 75 hertz. I would hear nothing of 113 hertz. A lot of 150 and nothing of 188. So it's kind of crazy. So you'd hear no odd harmonics and lots of even harmonics. So the smaller the room, the higher these frequencies are, which means they creep in. So this is a 15-foot room. So it's 37, 75, 113, 150, 180. But remember, if I was like at a 10-foot room, it was something like 56 hertz. We'll just say it's 50 hertz. So it'd be 50, 100, 150. Like it's way up there. And so you can really start to hear these things a lot. So it's really bad. So, okay. What about this? What about optimal? So okay. So this, what I'm hinting at here, not even hinting at, what I'm saying is that this situation sucks. This is a bad situation. So how do we deal with this? How do we remedy this situation here? So what we could do, one idea would be to, absorb them. But let's just talk about this, how do we deal with these things? So optimal room proportions. So rooms always exist in modes always exist in small rooms. Small room is where the room modes are in the audible range. So if I were to do this with, say, a concert hall, and if I say I have a 50-foot wide concert hall and I do the dimensional and I do the room modes on this, the room modes are going to be like 5 hertz for the fundamental, which means it's going to be like 10 hertz, 15 hertz, 30, 20 hertz. So all the modes of oscillation, they're so low that these room modes, they exist, but they're so low they're outside of the audible range. So this only really happens in small rooms where the room mode frequencies are in the audible range. So that's why we kind of define small rooms. So if we can't get rid of them, how do we deal with them? So try to distribute the axial modes so they don't overlap much. So overlapping modal frequencies cause extreme modes. We'll see what this means here in just a second. So modes higher than 200 hertz tend to not set up standing waves. So diffusion, absorption, and plus around 200 hertz, we can really add a lot of absorption and diffusion. We've just seen that from earlier in this last couple weeks. So we can deal with higher frequencies. It's those low frequencies that are just so hard to deal with. So let's take a look at this first example. So if I want to distribute these things, what I'm going to do here, so rectangular rooms tend to have the best sound. Square and cubic rooms are really bad. And we'll see this why. So the problem is with box rooms is that it's good economy of construction. So we have right angles, but so good economy. So we want to use economy of space. So if I put up a wall, it's going to be rectangle because I want just my rooms to be even. But the cool thing is with that is that room modes are easy to calculate. So it's just a simple, basically I just draw it out on a piece of pencil on paper, and I can calculate the room modes with just sometimes in your head. But with a basic phone calculator, you can just whip this up in no time. So how do we figure out what's good? So what we're going to do here, so this is axial distribution of 8 different rooms right here. So the length, the width, and the height modes of the heart. So all we're looking at is the axial modes. And what they did here, so this is A, B, C, and D. These are 8 different rooms. And what we did, and it doesn't really say what the frequencies are. Oh, yeah, I guess it does down here. So it's 0 to 50. So this is plotted on a linear scale down here. And what we did is, if I look at they give the dimensions of the room in the book, but it doesn't really matter for us right here. But what we can say is that this is like the first mode of oscillation in one axis, the first mode of oscillation in another axis, the first mode of oscillation in the third axis. So what we're doing is we're just plotting these so we can see how they visually line up with one another. And what happens here is what we want to see is we want to see distribution of our room modes. We don't want to see tight overlapping, or sometimes like right here, see where it says 2? That means this one has 2 of them that are overlapping directly on top of one another. And that's bad, which, I mean, you can also note this as the height of the wave, but it would show that this is much taller. So that means at this frequency, which is like at whatever, this is like, this number right here is 150, it's about 175 hertz. So that means in 2 different axes, it's going to be extremely, 175 hertz is an extreme amount of nodes and antinodes. So it's going to create really big hot spots and dead spots in that room. So kind of what we're shooting for. And so you can do this in your own room. And this one's got 3 overlapping. This room is terrible right here. Well, these are actually pretty good, but this bit is terrible right here. What we're kind of looking for is spread. We want our modes to be spread out. And so that's kind of that's ideally. So you can do this with your own control room or your bedroom or wherever you do your mixing. Measure this out and go, oh, okay, do a room mode analysis on here. And you can just do it with a spreadsheet, and you don't have to draw the plots here. I mean, it's kind of cool to draw them on as a plot, but you can just do it as a spreadsheet. It's just kind of harder to see. And the result is what we're looking for here is okay, so what we want even distribution of these around the space. So sometimes, you have to work, you don't have the choice. You have a room that's already built and you're working in this room, and it is what it is, and you have to deal with it. But if you have the chance, if you're building out a room, and so I do this when I build out my studios, I actually go through and I do this analysis right here. So I do the Sabine's formula and I do this one to figure out how's this room going to work. And so I use Sabine's formula to figure out the reverb times and the frequency of stuff. And I use the modal analysis to figure out the low frequency stuff. So that's kind of how I approach measuring and ringing out a room. So let's take this one right here. So they call this Bolt's range. I call this the pork chop. So this is a plot right here. And this came out a few years ago in a paper. And what they said here is basically looking at favorable room dimension ratios. So what we're looking at is the ratio of the length, the width, the height of a room. And if it falls within this pork chop right here, or a weird looking South America, I guess, no, it's more like Africa-ish. It's kind of like this, or I'll just call it the pork chop. Don't call it the pork chop out of, oh, sorry, no, you asked about splayed walls. We're going to talk just about that here coming up in just a few minutes. So I will address that exactly. So what what we're like, again, don't call this thing the pork chop outside of this class because nobody else will know what you're talking about. This is just what I call it right here. So this is just some stuff. But what we did here is we're looking at the ratio of the length of the room to the width of the room to the height. And what we're doing is we call it normalizing the height. So this is all in ratios. So what we're going to do is say, if you're within this pork chop, generally speaking, that's going to be considered a favorable room dimension. And so these are like, so this one right here, they call it a height of 1. So if your height was at 8 feet, for instance, you divide, the way we normalize it, you take your smallest axis, which is usually height, and you're going to divide it by all the width and the length by the height value. I'll walk you through this. So let's do this right here. So would a 15 by 10 foot by 8 foot room, oops, I got my foot on the wrong side there. 8 foot room be considered a favorable room? So in other words, will it fit into this one right here? So what I'm going to do this is I'm going to go, okay, normalize all dimensions dividing by 8, the height value. So I'm going to divide 8 by 8, which is 1, because height is 1. I'm going to divide 10 by 8, which is what, 1.2, yeah, 1.2. And then 15 divided by 8, which is, I don't know what it is. So let's look at this right here. The ratios become, so 15 divided by 8 becomes 1.875. 10 divided by 8 is 1.25, and 8 divided by 8 is 1. So again, what we're doing is we're normalizing this height to be 1. That's the term we're using for that. So we're creating a ratio. So on this ratio right here, now I go on my length, which is going to be 1.875. So I go up to 1.875, which is about right here. And I go over to 1.25. So 1.25, which is going to be 1.2, it's 1.3, so that's right here. Nope. So it falls, actually it's right around, well, maybe it's a little bit right here. So, oh, it's 1.9. Yeah, actually it's right around where the E is. So this it's pretty close to this one right here. So it falls outside of this pork chop range. So what that's indicating is that those harmonics of those modes are going to be, in one of these axes is going to be pretty close together, more comfortable, which is going to yield very hot and dead spots. So in other words, so this one says, no, this isn't within Bolt's area. It's not within inside the pork chop. So this one falls right outside about E. I don't know what the golden ratio. What is the golden? No. So what is the golden ratio again? I can't remember what we could do it. Let's try the golden ratio. Yeah. Does anybody remember off the top of their head? That would be interesting to know, though. The good question, though. Okay. So how about a 12 foot by 9 foot, 10 foot by 9 foot room? So you can do this on your own one. So I'm using feet, obviously, right now. But the cool thing is it doesn't matter if we're using feet or meters because they're just considered ratios. So if I did a 12 foot by 10 foot by 9 foot room, let's do that one right here. So normalize all dimensions by divided by height value by 9. So maybe you have a 9 foot room. So the ratios become 1.3 to 1.11 to 1 because I divided 12 by 9, 10 by 9, and 9 by 9. And so I end up with 1 to 1.11 to 1.33. So I'm going to go over here, 1.33, which is about, whoops, yeah, so I'm not even in here, 1.1. So that's way down here. So 1.3 is like right here. And 1.1 is like right here to 1. So nope, that's also bad. Nope, this room isn't good either. So what is? And so you just have to go through and do this measurement, and you can mess around with your height, your width, and your length to find out if you can get within this room right here. And so this isn't a hardcore rule of thumb. This is just something you're trying to shoot for. Like I said, a lot of times you move into like spaces that already have rooms built. But if you have the chance to build out your own control room, this is something to consider. Like you're going to try to manage this thing in here. Okay, so let's talk about splayed room surfaces here. So we talked about splayed walls before. So when we talk about splayed, you'll sometimes hear people about splaying walls to break up room modes. False. This is dead false. Splaying helps with flutter and diffusion, but not with room modes. Modes still exist, but they're warped, and it can be difficult to predict. So we'll take a look at some examples here. When you walk into like we talked about this, like when we were talking about like flutter echo and back earlier in the semester, and so if I had a snare drum and I'm playing the snare drum in the room, it's going to be, the echo is going to be going brrr, and it echoes back and forth and back and forth and back and forth. But by splaying the walls, it's gonna make the sound bounce around the room. In other words, diffuse that echo so that the energy's in the room, but it's not reflecting back and forth in there. So again, so people have this misconception that splaying walls also breaks up the room modes. It affects them, but it doesn't destroy them. So the modes still exist, but they're warped. So remember, so what this is like, this is looking a top down at the like we call these contour lines of the 100 mode. So in other words, before they were calling this 1 and this one's 0, but now we can say this is 100. We call it percent, 100%, and this is 0. So what it's doing is it's dropping down in. Remember, this is like dropping down in this axis right here at 34 hertz. So if the width of this room right here corresponds to 34 hertz, which we could figure out the length of the room, it's probably, I don't know, this is probably a 15-foot wide room. So if this is a 15-foot wide room, and so now if we switch this over here and we splay the walls out here, we'll see that we have, essentially, we get a positive 70 right here, a positive 40 here, and then a negative 100 here. So this is a weirdness. So because this is obviously, this is high, this is an antinode, node, antinode. We still have an antinode, node, and antinode, but it's now warped through the room right here. And it gets not as hot here, and it only gets up to about 40% or maybe 50% right here. And this one goes way down, all the way down here. So you still get the room mode. And so it's going to be hard to draw this out. This is something you have to use fancy software for. You can't really do this like with your brain. You have to use like, they have stuff called like, I don't know what they call the software, but it's like, there's some specific special acoustic software for doing this sort of thing. So if you're working with irregular surfaces, so if we go up to like the second, this is the 130 mode. So it's the third mode in this axis, the first mode in this axis right here. That it's the frequency is 80 hertz. That now all of a sudden we get these like islands of like weirdness. So this is an antinode, node, antinode, node, antinode, and as I walk around the room. So what we're saying, the point being here is that it doesn't really, it warps the room modes, but it doesn't break them up. They still exist. So in a 040 mode right here. So this is the fourth mode of oscillation in this mode, and then 0, and then 0 in the height, that we can see that it just kind of messes things up. So we still have them. And you can kind of see the general shape. It still kind of correlates to this one right here, but you got these kind of weird islands of stuff in there. And then I guess another 5x7 meter room at the 300 mode. So it's 102 meters for the third mode of oscillation. And you get these kind of hot and weird dead spots. So they still exist. So what are we to do about this? This creates some real problems here. So absorption is oftentimes the best solution. But if you recall, when we were talking about absorbing, just generically absorbing regular, like with foam, it doesn't work because the wavelengths are too long. So what we have to do is we have to do these tune absorbers, so the panel absorbers or Helmholtz resonators. So you basically figure out the room modes, and then you just go and you develop an absorber, like a diaphragmatic absorber, based off of that room mode, and you put it up in that axis. And what it does is it damps down those room modes and absorbs them so that it basically controls those room modes. It's hard, but it works pretty well. So we can use diaphragmatic absorbers, which we call panel absorbers, or Helmholtz resonators. That's another popular one right there. But these are both tuned to a single frequency. So you have to tune these. And so usually you're going to tune these to like the lowest mode of oscillation. But if you're really sophisticated, you would tune them to probably the first mode and the third mode and the fifth mode, like, because those are the ones that are going to have like really dead spots in the middle of the room. So this is a real problem for almost all small spaces. And this is indeed an issue. So we have like 10 minutes here. So let's take a look at this. So when you do, I guess the other thing I should say is, let me go back. I want to do one more discussion item here. I'm going to share another whiteboard. Let's clear this one out. Clear all drawings. So what if you have a room that's shaped like an L? So how do you do a modal analysis on this one? Well, you're going to do an analysis in this axis right here. Actually, let's and change colors. I'm going to do a modal analysis for this one right here, a modal analysis for this one right here, a modal analysis for this one right here, a modal analysis for this one for right here. Because you're going to have oh God, what is it? It does something bizarre when I like when I drag it from one screen to another. That's very strange that it pauses that. Thank you for doing that. Tell me that. Okay, so if I have an L-shaped room right here, so the red lines are going to be the modal analysis. Let me undo that so I can draw that again. So if I have an L-shaped room, what I'm going to do is I'm going to do a modal. I'm going to figure out the length in this axis right here. Do the modal analysis for what F1, 2, 3, 4, 5 in this axis. Do an F1, 2, 3, 4, 5 in this axis. F1, 2, 3, 4, 5 in this axis, and F1, 2, 3, 4, 5 in this axis right here. So, and then I'm going to plot those out and go, okay, can I see that? And then what will end up happening is, yeah, if I'm walking around the space, I'm going to get some I'm going to have a node in this axis along this wall right here. So it gets kind of complicated, but it's a real world example. So if you have some like a weird shaped room, like you'll really get some strangeness, not strangeness, but difficult to predictness with that. So, yeah, so I mean, splaying walls makes it a little bit trickier to do this with. So if I were to let me go back and share my screen. And let me pull up RubyQ Wizard. I want to show you something cool here. Or what I think is pretty cool. Cancel. What we have over here is this room simulator. So if I click on this room simulator right here, what this is going to allow us to do is say, okay, if I'm working in feet, and I can put in the length, the width, and the height of the room. So in this case, it just gives me default value. So 16 feet 5 inches, 13 feet 1 inch, and 7 feet 10 inches as my room right here. So surface absorption. So these are my absorption coefficients. And it's just, it's not saying like per frequency. These are just kind of generic absorption coefficients. And I can say the room is sealed. Most rooms are going to have like leaky, like air. So it's going to change it, but I'll say this is more realistic if I have it not sealed. And what I have here, I'm going to go back down to one subwoofer. So this is my head right here, and this is my subwoofer. So what we see here is this shows the effect if I move my subwoofer around the room. So say I have my main right here. And so this is showing us from 20 hertz to 200 hertz. Because above 200 hertz, room modes, like you can see they're getting really dense. Above 200 hertz, we can really absorb stuff using absorption stuff. And if I'm sitting here, so this is looking down on the room, this is looking in the room, like through the room. And I have my subwoofer on the floor, and I have it kind of like, maybe I have my main left, my main right, and my subwoofer sitting underneath my desk that I'm sitting at right here. The result is, if I'm cranking out some sounds here, that if I walk around this room, if I walk to the edge of the room, we'll see that this is, let's see, do they have modal resonance lines? So I'm not going to care about tangential as much right now and oblique. I care about the axial. So the red one is my axial one. So this is my first mode, my second mode, my third mode, and my fourth mode of my axial in probably my floor to ceiling height right here. This green one right here is going to be my width. Oh, sorry, I guess blue is height. Okay, yeah. Starts with the highest one up here. So the blue one is the length. So that's going to be this mode of oscillation right here. So if I walk around this room and I go to the edge of the wall right here, I've got an antinode right here and a node right here and an antinode right here and a node right here. But then the green one, you can see as I walk around the room what I'm going to experience. So if I go into the corner of the room right here, we're going to get some very big antinodes, like everything's kind of high up. But if I go to the middle of the room, we're going to see that right in the middle of this room right here, it drops so big right here that I'm not going to be able to hear anything. And so you can see the effect of just walking around this room, the low frequency effects of this. So, and then even if I move my sub, so the modes don't change, but how much it's exciting each of the modes, the frequency of the modes don't change because the standing waves don't change, but the amount of different modes that is exciting is going to be, it will affect this. So your subwoofer does affect this thing. And so if I flew my subwoofer at head height, or maybe you have really big main speakers that have that are up there, you're going to have some pretty big differentials. Let me put that back on the floor. So we can see that right here, this is like what, 70 70 dB, and this is all the way down to 36 dB. So that's a 36 dB differential between the two of those. That's a lot. So again, this can be some problem. So we can also mimic other things. So what else could we do with this? So let's add, I can add a second sub in there. So if I had two subwoofers, so the room I'm in right now, I have two giant subs behind my desk over here. They're about like right here. Actually, let's see, my width of my room, let's do this as 12 feet inches. My length is about, it's about 17. And the height is about 9-ish. So this is the room I'm sitting in right now. This is about what it looks like for me. And I'm sitting about right here. Yeah, maybe these are further back. They're about more like that. So the reason I have two subwoofers is because they help mitigate some of the modes in this axis right here. But yeah, you can see we have a real problem at around 45 hertz and some spikes here. So this could cause some problems. So if I were in this room right here, what I would do is I would be like, okay, well, the width of my room is these green ones right here. And there's some real problems with these ones right here. So what I would do is I'm going to need to add, actually, what if I did this? What if I added a third subwoofer into the room? And I'm going to put this one behind me over here. That'll help smooth things out a little bit, because now it's going to help manage the axes here and manage it here. Because basically, if this is a positive antinode, and this is like if I put this here and this one here, the result is that this one is going to be in the positive and this one's going to be in negative, and they cancel each other out. So having more subwoofers is a really useful tool for helping control room modes. And then if I had a third one in the back behind me here, that's another way, which actually I'm considering doing. I have an extra driver, so I was going to put this in the room behind me. But we can see that this definitely has some real problems. And this is why you need to go through and test this stuff out. So usually the way I do it, I don't usually use the simulator right here. I basically just go through and do the math with modal analysis. And then I go with my Room EQ wizard here and I start doing some measurements. But I'm just going to open up that one that we did before. Oh boy, I don't know if I have any room modes measurement analyses in here. Let's just use, where is that? Acoustics. I'm just going to open that one that we were using before. What happens for most people, let's just look at SPL right here. Let's just look at one of these, is that when we look at the room analysis of this, when most people do these things, what they'll see it's pretty smooth and flat up here, but then as they get to these low frequencies, you'll see massive spikes. And what people tend to freak out about is they're like, my speakers suck. You're like, no, your speakers are fine. It's your room modes that are crazy. And so armed with this information of doing a room mode analysis, if I put my measurement mic all the way against the wall, I should see some giant peaks right there. And if I put it in a node, I should see some giant like valleys. And so when I go over to my waterfall, for instance, and I generate this, what you'll see is that the room modes really, you can see these things ring out. Let's drag this down a little bit. Oops, other way. And what will end up happening is that these room modes will act like giant fins because they ring out for a really long time. So again, doing absorption is low frequency absorption is going to be the tool of choice for controlling these room modes. So generally on the high frequencies up here, you're going to use absorption and diffusion to tune. Well, first you want a flat speaker, but then you can use absorption and diffusion to tune this stuff. And then you're going to use diaphragmatic and low frequency absorbers to tame the room modes down here. And the smaller the room, the higher up these room modes really influence it. And then the higher the larger the room, the lower the frequency those room modes are really going to affect it. And it's an understanding between this relationship between the room modes are going to affect the low frequencies, and just reflection and reverberation are going to affect the high frequencies, that over time you're able to start to like develop this acoustic picture of a space. So that's all we really had for today, but that's it's a lot of stuff. There's a lot of information packed in there. But getting comfortable with these room modes is super, super duper important. All right, so the next homework is going up today. It's going to be due a week from today. And other than that, my friends, go enjoy the awesome day outside. It's super sunny, and have a killer weekend. And I will see you all for next week. We have one more week until spring break. Yay! And then we have some spring break. So, All right, my friends, I will stick around for office hours, but if anything else, I'm gonna stop recording, and I will see you all later.